Okay, so we're going to cover 2.7, which is all about graph transformations. So we're going to start out with covering reflections, then stretches and shrinks, then shifts, and then we're going to put that all together to kind of see how do we graph based on this. We'll be using the 2.6 graphs as our starting points. And then we'll kind of do something in the reverse form where we go from a graph and try to build the function back up from what the graph was given. So for our first kind of notes here, we're going to say, suppose we had y equals negative on the outside of the function of x, or y equals the function evaluated at a negative x. If the negative is on the outside of the function, where this function would be like one of the 2.6 functions, like maybe it's square root of x or x squared or absolute value of x, this does what's called an x-axis reflection. If the negative is inside where the function's being evaluated at, this will do a y-axis reflection. And so we'll do a quick example where we want to sketch just want to sketch some of the functions with reflections only. So we're going to kind of do only reflections and only stretches and shrinks, then only shifts, and then we're going to put them all together where we're doing multiple things. Oops, I got the T and the C backwards. That's T, so sketch, that looks better. So part A, we want to sketch y equals negative x squared. Part B, I want to sketch y equals negative inside of x cubed. And part C, I want to sketch y equals negative square root of negative x. So for part A, the negative is on the outside. So this is going to do an x-axis reflection. I'm going to draw my starting function, x squared, in with the dotted line. So this is my dotted kind of beginning graph. And again, we want to kind of note x squared goes through points negative 1, 1 and positive 1, 1, and the origin. So whenever I reflect, do an x-axis reflection of this, I pretend like there's a mirror along the x-axis, and this top part is reflected and becomes the new lower part. And this right-hand part here is reflected downwards and becomes the rest of the graph heading downwards. In this graph I've drawn with the solid line, this is the graph of y equals negative x squared. For part B, we start with a cubic, and since the negative is inside, this time this is going to do a y-axis reflection rather than an x-axis. We kind of base it around where are things with reference to the parentheses for the stuff cubed. This negative is inside the parentheses of stuff cubed. If the negative was outside, then it would be written kind of like we have here. So this is a y-axis reflection. So we'll start with x cubed's graph. We'll draw it kind of dotted. X cubed's graph passes through the origin, passes through the point 1, 1, and also passes through the point negative 1, negative 1. So these are a couple points we know are on the graph. For a y-axis reflection, you pretend like there's a mirror along the y-axis. It's going to take this right-hand arm here, this right-hand side, it's going to reflect it around the y-axis, and that's going to become our new left-hand side. So this right-hand part right here reflected, became the new left-hand. This left-hand part down here reflects and becomes my new right-hand side. And so that's our graph, part B, y equals negative x cubed. Part C, we got our expression looking like this. We start at the origin and we have our graph looking like that. That's the square root graph. we have both an x-axis as well as a y-axis reflection in this case. So we have both reflections. So let's do the x-axis first. So this dotted line that was here is going to reflect about the x-axis. I'm going to draw it in with a different dotted pattern. So this is what it looks like. What became the top expression of our function now looks like this. And then we take this, after the x-axis reflection, we reflect that about the y-axis. So starting at the origin and heading down and to the left, this is the final form of my graph. Okay, so that is some initial things on reflections. Next, we need to talk about stretches and shrinks. And I'll use, like, for this class, str/shk for stretch or shrink. So for this, we're going to let a be a number bigger than 1, and we're going to let b be some number between 0 and 1. So we'll have y equals a times f of x, and we'll have y equals b times f of x. We'll also have y equals f of ax, as well as y equals f of bx. Now, if you're outside, this does vertical stretch stuff, so this will be a vertical stretch. And if you're outside, it works the way you want it to. If a is a number bigger than 1, this does a vertical stretch by 2. If you're outside, this does vertical stretch or shrink. If you're a number between 0 and 1, like your fraction, like a half or a third, this does a shrink. And it does, whoops, I wrote vertical stretch by 2. It should be vertical stretch by whatever the a value is. So this is a vertical, like if a is 2 or a is 3, this would be a vertical stretch by 2 or 3. So if b is a fraction, like a half or a third, this will be a vertical shrink by the b value, like a vertical shrink by a half or a third. If you're inside, it's horizontal and it works the reverse of how you'd expect. So inside, this is horizontal. If you have a number bigger than 1, this does a shrink by 1 over the number. So like, if you had a 2 in there, that would be a horizontal shrink by a 1/2. Or if you had a 4 in there, that'd be a horizontal shrink by 1/4. For b, this does horizontal, and this will be a stretch by 1 over b. So if b is a half, it's actually a horizontal stretch by 2. Or if b is 1/5, it's a horizontal stretch by 5. So we're going to do a quick couple of these just to see what does a horizontal and a vertical stretch look like. Part A, we want to do y equals 2 absolute value of x. Part B, we want to do y equals 3x squared. Part C, we want to do y equals 2, sorry, let's make that 1/2. 1/2 of 3x cubed. So comparing what we got here, let's label all 3 of these first, then we'll sketch them. We have a 2 out front, outside is vertical. It works the way you want it to, so that's a vertical stretch by 2. Here where the 3 is inside, this is horizontal. Horizontal works reverse of how you'd expect. You'd expect that to be a stretch by 3, so it's a shrink by 1/3. Then this one has 2 things. Outside we're vertical. Outside works the way you want, so it's vertical shrink by a half. Inside we're horizontal. And horizontal works reverse of how you'd expect. This is going to be a shrink by 1/3. So we'll go through and sketch these. Absolute value is our starting graph here. Absolute value just looks like the V shape. And on absolute value, we know a couple of dots. We have -1, 1, and we also have 1, +1. When you do a vertical stretch by 2, what you do is you multiply all the y values by 2. So the origin stays put because it has a y value of 0, and 0 times 2 is still 0. But this point here that had the y value of 1, that gets moved up here to 2, because you multiply 1 by 2. And this one here gets moved up to 2 also. And then what you're going to do is basically just try to double everybody's vertical distance. So the point out here that was at 2, it now has a y value of 4. The point out there that was a y value 3, it now has a y value of 6. So you're going through and you're doubling everyone's vertical distance. And the solid line that we drew there, that is what our graph would look like after the vertical stretch by 2. So on this next one here, let's see here. We start out with x squared. So x squared is our basic function here. Looks kind of like that. And we have the point -1, 1 and +1, 1 are both on it. We want to do a horizontal shrink by 1/3. So what this does is it crunches all the horizontal distances down to 1/3 of what they were. So this point that used to be out here at x equals 1 now comes back into x equals 1/3. And the point that used to be out here at a horizontal distance of -1 gets crunched down to a horizontal distance of -1/3. The origin had a x value 0. 0 times 1/3 is still 0. And we connect the dots with our parabola shape. So we basically have a parabola that's been crunched horizontally, which made it kind of narrower. All right, this last one here. So we start out with the graph of x cubed, which looks like this more or less. We have following points. We have -1, +1 is a point that falls there. Sorry, +1, positive is a point that falls there. The origin's on it. And we have -1, -1 is down here. So first let's do the vertical shrink by half. What the vertical shrink by half does is it says, look at everyone's y values. You're going to cut the y value by half. So look at the y value down here at -1. You're going to cut it back by half. So the y value that was out there at 2 comes back down to 1. And what you get is basically a flatter cubic from this operation. Okay, so we got our flatter cubic. So now we want to do a horizontal shrink by 1/3. So on that flatter cubic, what the horizontal shrink by 1/3 says to do is this point that was here, pull it into 1/3 of its horizontal distance. So the point that was there, pull it into 1/3 of its horizontal distance. And now redraw your cubic. And so that it's a little cluttered. What basically happens here is we started with our base graph. The point was at 1, 1. It went back to a half. Sorry, it went to a vertical distance of a half and then pulled in a horizontal distance of 1/3. And that got us our first curve, our upper curve. And then the point that was at -1, that point we pulled it, cut its distance in half, pulled it in to 1/3 of its horizontal distance. And that's where the rest of the graph went. So they kind of worked against each other, but the end result is you end up slightly narrower than you started. Okay, so that is how stretches and shrinks work. Next, we need to talk about shifts. So for shifts, we have forms y equals f of x plus c, y equals f of x minus c, y equals f of x plus c, and y equals f of x minus c. When you add c out here, this shifts your graph up. When you subtract c out here, so it should be, sorry, it's up c units. When you subtract c, this moves your graph down c units. When you're inside, stuff still works backwards from how you'd expect. Adding c inside moves your graph to the left c units, and subtracting c inside moves your graph to the right c units. So you got your shifts like that. We'll do a couple quick examples. Let's say we want to graph for the first example, part A, we want to see what is y equals x plus 2 squared. Part B, we want to see what's y equals square root of x plus 1 minus 2. And we'll just graph these two. So for y equals x plus 1 or x plus 2 squared, we identify that since we're adding 2 inside, this is going to move our graph to the right. Sorry, just kidding, it works backwards from how we expect it to. We expect it to move us to the right because it's adding. It actually moves us to the left because we're inside, and stuff inside works the reverse of how we'd like it to. So if our base function here is x squared, and that graph looks like this, then you're going to scoot that graph 2 units to the left. So we go to the left 1, 2 units, and then we just redraw our parabola the same shape that we had there. And that'll be our answer graph. So our starting graph is the dotted line, the answer graph is the solid line. So over here, we would start with a square root graph, which looks kind of like this. If we add 1 inside, that moves us to the left 1. If we then subtract 2, subtracting 2 is going to move us down 2 units. So we want to go left 1, down 2. So we go left 1, we go down 1, 2 units. Left 1, down 2 is down here. And then we're going to connect through with our square root graph. And that'll be what that graph looks like. So putting this stuff together, we're going to do a couple where we kind of put all these ideas together. When you have stretches, shrinks, reflections, stretches, shrinks, and shifts all mixed together, you're going to end up getting an order of operations that you need to do. So there's an order to these. So we'll say order of operations. And the order of operations, transformations. So for the order of transformations, first we need to do reflections. So it doesn't matter if you do the x-axis reflections or the y-axis reflections first, as long as before you move on to anything else, you get the reflections out of the way. Second, you got to do stretches and shrinks. Again, doesn't matter if you do like horizontals or vertical stretches first or second. You need to work on them after you get done with the reflections and before you move on to the shifts. And third is the shifts, so these are done at the end. So we're going to make up an example, and we'll go through and get it graphed. We're going to kind of pause on part 1 there, and then I'll finish recording it here a little bit later. I have another class about to start. So for this example, let's say we want to sketch. Let's say y equals -2, let's say square root of x plus 2 plus 1. So there are 4 transformations here. The initial negative is going to do an x-axis reflection. The multiply by 2, that's outside of the square root, so that's vertical. Outside stuff works how we like it. It's a vertical stretch by 2. We add 2 underneath the square root. When you add 2 underneath the square root, that's going to move you to the left 2 units. And then adding 1 outside. When you add outside, this works back the way you'd like it to. This is going to move your graph up 1. So I'm going to have kind of a scratch work graph where we do most of our stuff, and then we'll move the leftover answer there. We'll move it and redraw it nicely over here. So my starting graph is square root of x, which looks kind of like this. Starts at the origin and trails off, and I knew that from memorizing my 2.6 information. I apply an x-axis reflection to it first, so that gives me a curve that kind of looks like, if I draw it better, well, I keep doing that shape there, kind of weird. So we'll draw it with a slightly different dot pattern. This right here is where we're at after the x-axis. I have to do the x-axis first, then the stretch and shrinks next. Then at the end I do the shifts. So this is where we're at after we do the x-axis reflection. So the original graph had the point 1, 1 on it. This graph has the point 1, -1 on it. And now I want to do a vertical stretch by 2. So that's going to double the vertical distance. So my point here that was at a distance of -1 is now at a distance of -2. So I have kind of a taller square root graph that is opening downwards like this. So then I want to take that shape, I want to move it left 2 and up 1. So we go left 2 units, we go up 1 unit, and I'm going to redraw this taller graph here. So we're going to redraw the taller graph, opening downwards and pulling off to the right. And this will be my answer graph here. So we will stop on part 1 here. So stop on part 1 of our videos here. We'll pick up the rest in just a minute. Okay, let me make that look like a 1 instead of a 2. So part 1 stops there.